Hello, welcome to this, the second in a sequence of tutorials about cardiopulmonary exercise testing. My name's John Carlisle. During this, the second tutorial for novices, we're going to briefly talk about peak oxygen consumption, and then the first part of identifying the anaerobic threshold. So the first thing to do for me is to clear up the screen a little bit. And we're going to draw what's happening during a cardiopulmonary exercise test as performed in the preoperative assessment clinic. So the patient is sitting on a bicycle. We are measuring a few things. And the patient sits on the bike, not doing anything for a little while whilst recording some stuff. Then they pedal, but without any braking on the bicycle, for 3 minutes. And then they pedal against an incrementally increasing resistance for about 10 minutes. During the incremental phase, this 10-minute period, the braking goes up linearly on the flywheel in the base of the cycle ergometer, and that causes the person pedaling to exert more power in watts. So the joules per second, which is what a watt is, will go up linearly. And to fuel that increasing power, the person's oxygen consumption will also normally go up linearly as well. And I hope that you'll remember the fixed relationship between oxygen consumption and power is that for each watt increase in power, the oxygen consumption goes up by 10 mils. During the freewheel phase, the oxygen consumption has increased about double from the oxygen consumption needed to keep the patient upright, but not pedaling. So during this first phase, we have some oxygen consumption, and that's what's necessary to maintain body posture on the bike. Then the patient starts pedaling here. Oxygen consumption goes up, about doubling, although more in people who are obese. It reaches an equilibrium, and then about 1.5 minutes after the onset of power, external load here, the oxygen consumption goes up linearly. Now during this time, the carbon dioxide output is also going to go up. In the aerobic state, the carbon dioxide output is usually somewhat less, maybe about 80% of the oxygen consumption, and it will carry on in that relationship until we get a surge in carbon dioxide caused by the supplementation of aerobic ATP production with anaerobic ATP production. So just here, which is the point we're going to be interested in identifying, the carbon dioxide output increases, and the fixed relationship, or relatively fixed relationship, between oxygen consumption and carbon dioxide is broken. So we're looking for this point here. However, this graph I have drawn for you is not the best place to identify the anaerobic threshold, so we need a different plot. Before doing so, I'll just remind myself to talk about the peak oxygen consumption. The peak oxygen consumption is the highest value of oxygen consumption measured, usually over a 20-second averaged period, and it's usually at the end of the test. Occasionally people may have a peak value up here and then sort of level off. The purpose of averaging is to avoid spuriously assigning the peak oxygen value to an outlying dot somewhere up here. So we want averaged data, and usually around about 20 seconds worth, to reliably identify the anaerobic threshold. So reliably identify the peak oxygen consumption, I should say. So going back to the anaerobic threshold, how are we going to identify that? So the plot we mainly want for identifying the anaerobic threshold is this one, where the vertical axis is carbon dioxide output and the horizontal axis is oxygen consumption. And we would like the scales to be the same. So the distance between 0 and, let's say, 1,000 is the same on vertical and horizontal axes. And why we'll come on to in a bit. So at rest, the patient was using up some oxygen to maintain body posture on the bicycle. They were outputting a little bit less carbon dioxide. So where these two values intersect, oxygen consumption, carbon dioxide output, we're going to draw a dot. And that's reflects the oxygen consumption and the carbon dioxide output at rest. As the person uses up more oxygen because they're working harder, they're also going to output more carbon dioxide. For each unit of additional oxygen output that goes up, the carbon dioxide output will go up a little bit less. Remember, the ratio is less than 1. So let's plot these sequential dots, and there's going to get a point where the person's muscles are going to supplement aerobic ATP production with anaerobic. We'll get a surge in carbon dioxide, so the dots are going to go northwards. So all we need to do to identify the anaerobic threshold is draw a regression line, linear regression line through the first set of dots before the anaerobic threshold, and then the set of dots after the anaerobic threshold, and where they two cross, that is the anaerobic threshold. Now the anaerobic threshold is framed in terms of the oxygen consumption at that point. So the anaerobic threshold is going to be moles of oxygen per minute, or perhaps normalized to mass, moles of oxygen per kilogram per minute. And that's all there is to it. You can normalize the oxygen consumption to other variables, which we'll get to in an advanced tutorial at some point. However, for most of the tests, you're not going to get such a neat convergence of two linear regression lines. So let's plot out data that's a little bit more typical of what you will see. So we're going to have the same type of dots being plotted for oxygen consumption and carbon dioxide output. And you'll see, intentionally I've drawn dots that lie on a curve rather than on two intersecting straight lines. So we have a problem because it's difficult to determine where we should draw two straight lines. We could draw them there, or we could draw them elsewhere. We'll have intersections at a range of places on the horizontal axis, so our anaerobic threshold value is going to vary. So rather than do that, we modify the method. So the original method I showed you of two intersecting lines is called the V-slope method. So the original method was called the V-slope method, and now we're going to modify it. So unsurprisingly, this more common method that you'll see mostly in the preoperative assessment clinic is called the modified V-slope method. So let me draw my curving sequence of dots. How are we going to identify the anaerobic threshold here if we're not going to use two linear regression lines? What we're going to do, your software will allow you to on your machine, is we're going to bring in a cursor line. So this straight solid line is one produced by the machine, and on two axes that are the same scale, this angle here is 45 degrees, and this tangent is called a unitary tangent. What you do with your mouse is you drag that straight line in until it is touching your data points. Wherever it touches the data points, that's your anaerobic threshold. If you have, say, 3 in a line that touches that unitary tangent, you select the last data point to still be in contact with the line. Note the line doesn't go through the data points, it just touches them, and that is the value of your anaerobic threshold. So this was the modified v-slope method, where you bring in a unitary tangent, it touches your data points, the last data point in contact, the edge of the data point in contact is your anaerobic threshold, and again that will have a value of mils per minute or litres per minute, or you can normalise it to mass, mils per kilogram per minute. There are some supplemental plots that can be used to support your identification of the anaerobic threshold, and that's what we're going to come on to in tutorial 1.3. Thanks very much.